Today we're going to explore one of the most profound discoveries in condensed matter physics, the observation that led to our understanding of superconductivity. This discovery was made by Kamerlingh Onnes in 1911. In the early 1900s, physicists were intensely curious about how materials behave at extremely low temperatures. Kamerlingh Onnes had just succeeded in liquefying helium, reaching temperatures below 4 Kelvin. A fundamental question arose. What happens to the electrical resistance of metals as we cool them toward absolute zero? Classical physics suggested that resistance should decrease smoothly and gradually as temperature drops, because thermal vibrations of the lattice ions would be reduced. Some physicists even thought that resistance might reach a minimum value and then increase again due to impurity effects at very low temperatures. Kamerlingh Onnes chose to study mercury because he could obtain it in very pure form. He measured its electrical resistance as he cooled it down using liquid helium. Here's a simplified diagram of the experimental setup. The mercury sample is immersed in a bath of liquid helium. Electrical leads allow measurement of resistance as temperature decreases. The measurements span from room temperature, about 300 Kelvin, all the way down to approximately 4 Kelvin, an extraordinary achievement for that era. Let me show you what the actual data look like. We'll plot resistance on the vertical axis versus temperature on the horizontal axis. At higher temperatures, the resistance decreases smoothly and gradually as expected. Each yellow dot represents an experimental measurement. Above about 20 Kelvin, we see exactly what classical physics predicts. Resistance decreases smoothly as temperature drops. However, something completely unexpected happens when we cool below approximately 5 Kelvin. The resistance doesn't just decrease smoothly. Let's zoom in on the low temperature region to see what actually happened. This is where the Nobel Prize-winning discovery lies. Notice the dramatic change. Above 4.2 Kelvin, resistance decreases gradually. But right at 4.2 Kelvin, the resistance drops essentially to zero within an incredibly narrow temperature range. This is crucial. The resistance didn't gradually approach zero. It dropped abruptly, almost discontinuously. Below the critical temperature of 4.2 Kelvin, the resistance was so small that Onnes couldn't measure it with his instruments. It was effectively zero. Now let's try what any physicist would naturally do first. Attempt to fit the entire dataset with a single smooth function. Classical theory suggested resistance should follow an exponential decay, or perhaps a power law as temperature decreases. Here's an attempt to fit the data with a smooth, decreasing curve. Notice how this blue curve completely fails to capture the abrupt transition. No matter how we adjust the parameters, a smooth decreasing function cannot reproduce that sharp, almost discontinuous drop to zero resistance. If we calculate the residuals, the differences between the fitted curve and the actual data near the transition temperature are enormous. This fit is fundamentally inadequate. So we have to ask ourselves, why does every smooth-fitting function fail? What does this tell us about the physics? The failure of a single smooth function suggests something profound. We're not looking at one continuous process, but rather two completely different physical regimes. Above the critical temperature, mercury behaves as a normal metal. Its resistance decreases gradually due to reduced thermal scattering. Below the critical temperature, mercury enters a completely different state of matter, the superconducting state, where resistance vanishes entirely. Now we fit each regime separately. Above the critical temperature, we use a classical model. Below it, we use resistance equals zero. This captures the physics accurately. For the normal state, we can use classical models, like the Bloch-Grüneisen formula, which accounts for phonon scattering. For the superconducting state, there is no fitting needed. The resistance is precisely zero, not just very small. Now we need to understand why this abrupt change indicates a phase transition, a fundamental change in the state of matter, rather than just an improvement in conductivity. Think about water freezing. At 0 degrees Celsius, liquid water abruptly transforms to solid ice. The properties change discontinuously. Just as water doesn't gradually become more solid-like, mercury doesn't gradually become more superconducting. The transition is sharp and definitive. Phase transitions are characterized by what we call order parameters. For superconductivity, the order parameter is related to the density of superconducting electron pairs. Above the critical temperature, the superconducting order parameter is exactly zero. there are no Cooper pairs. Below the critical temperature, the order parameter suddenly jumps to a finite value. Cooper pairs form spontaneously throughout the material. Let's discuss why this feature was so resistant to classical modeling and what that resistance tells us about the underlying physics. Classical physics is built on the assumption that natural processes occur smoothly and continuously. Small changes in conditions produce small changes in properties. When we see discontinuous changes, this signals emergent phenomena, collective behaviors that cannot be understood by analyzing individual particles alone. Classical models for resistance typically involve exponential temperature dependence, where delta is an activation energy and Kb is Boltzmann's constant. Such models predict resistance approaches zero asymptotically, but never reaches it. They fundamentally cannot produce the observed behavior. Let's examine the transition more quantitatively to understand just how sharp this change really is. The transition from measurable resistance to zero resistance occurs over less than 1/100th of a Kelvin. This is extraordinarily narrow. The relative width of the transition, delta T divided by the critical temperature, is less than 0.003. This is an incredibly sharp transition. With modern techniques and purer samples, we now know the transition can be even sharper, occurring over microkelvins. When we zoom in extremely close to the critical temperature, the transition looks almost like a step function. This is the signature of a first-order-like phase transition. What were the implications of this discovery for our understanding of matter and physics more broadly? First, and most importantly, it revealed a completely new fundamental state of matter that had never been observed or predicted. It demonstrated that quantum mechanical effects, usually confined to atomic scales, can manifest in macroscopic samples of matter. It fundamentally challenged everything we thought we knew about electrical transport and resistance in materials. The experimental observation in 1911 created an enormous theoretical challenge that wasn't fully solved until 1957. The central question: why does resistance suddenly and completely vanish? What mechanism allows electrons to flow without any energy dissipation? The answer, provided by Bardeen, Cooper, and Schrieffer, is the formation of Cooper pairs, bound states of two electrons mediated by phonon interactions. These Cooper pairs are bosons, not fermions, and they can all occupy the same quantum state, forming what we call a Bose condensate. This condensate moves coherently through the material without scattering off impurities or lattice vibrations, hence zero resistance. Onnes went on to measure other materials. What did he find? Lead becomes superconducting at 7.2 Kelvin. It shows the same abrupt transition. Tin transitions at 3.7 Kelvin, again the same sharp drop in resistance. Interestingly, excellent normal conductors like gold, silver, and copper do not become superconducting, at least not at accessible temperatures. Here's a comparison of three superconducting elements. Each shows the same characteristic abrupt transition, but at different critical temperatures. The sharpness of the superconducting transition became a crucial diagnostic tool for material scientists. A very sharp transition indicates high sample purity and quality. Impurities and defects can broaden the transition. The width of the transition region measures sample homogeneity. A broader transition suggests compositional variations. In modern high-quality superconducting samples, we can achieve transitions that are only microkelvin wide, demonstrating extraordinary material control. Let's address a deeper question. Why is it impossible to smoothly connect the normal and superconducting regimes with a single model? The normal and superconducting states have fundamentally different symmetries. The superconducting state breaks gauge symmetry spontaneously. The superconducting order parameter is non-analytic at the transition point. It cannot be expanded in a smooth Taylor series across the transition. The magnitude squared of the order parameter psi is exactly 0 above Tc and finite below Tc. This is a true discontinuity. An energy gap opens up discontinuously in the electronic spectrum at the transition. There's no gradual gap formation. The precision of Onnes's measurements was crucial. If the transition had been measured less carefully, the discovery might have been missed or misinterpreted. Onnes achieved temperature control better than 1/100th of a Kelvin, which was extraordinary for 1911. His resistance measurements were accurate to better than 1%, allowing him to see the dramatic drop clearly. He performed multiple measurement runs, confirming the reproducibility of the transition and ruling out experimental artifacts. From our modern perspective, we can appreciate just how revolutionary this discovery was. This discovery essentially opened the entire field of quantum materials, where quantum mechanics determines macroscopic properties. It hinted at the role of topology in physics, something we now understand much more deeply with topological phases of matter. It showed that emergence, where collective behavior cannot be predicted from individual components, is a fundamental principle of nature. The discovery of superconductivity has led to numerous practical applications. Medical imaging, specifically MRI machines, rely on superconducting magnets to generate strong, stable magnetic fields. Particle accelerators like the Large Hadron Collider use superconducting radiofrequency cavities and magnets. Modern quantum computers often use superconducting circuits as qubits, exploiting the unique quantum properties of the superconducting state. Let me summarize the key insights we've covered about this discovery and its analysis. The central observation is that the abrupt drop in resistance fundamentally resists fitting with any smooth, continuous function. We must treat the system as having two distinct regimes, each with its own physics. This is not a mathematical convenience, but a physical necessity. The sharp, discontinuous nature of the transition signals a true phase transition, a fundamental reorganization of the quantum state of matter. This discovery revealed an entirely new state of matter, whose properties emerge from quantum coherence on macroscopic scales. Without Onnes' exceptional experimental precision in both temperature control and resistance measurement, this discovery might have been delayed by decades.